Thank you, everyone, for joining for Advaith's dissertation. It's very exciting. Advaith was the first PhD student recruited in the Frog Lab, and now officially the first Frog student defending his PhD thesis. So it's a big moment for Advaith, but also for the entire lab, which is very exciting. So we've had a lot of chances to do fieldwork together and late research paper editing as well. So it's been a fun time, and I'm excited to have Advaith present his PhD research to you today. Just some logistics. There is a final in this room immediately after, so we are going to have to end right at 1 p.m. sharp. So if everyone can save questions, unless they're critical to the end, then we'll get to questions at the end. But I will let Advaith take it away. Thank you.
So hello everyone, my name is Advaith Sethuraman, and today I'll be walking you through my thesis dissertation defense titled Deep Learning Methods for Autonomous Underwater Survey, Reacquisition, and Close Range Inspection. Okay, so the process of finding and inspecting submerged objects is very challenging due to the vastness and hostility of the ocean. From the marine archaeology side, we have shipwrecks, like those right in our own backyard in Michigan, that hold significant cultural and historical value. Search and rescue applications are also an important application area. For example, the OceanGate Titan submersible, which experienced a catastrophic decompression a few years ago, ironically while visiting another maritime disaster, the wreck of the RMS Titanic. Discovery of black boxes, inspecting the wreck, and understanding what happened are crucial to ensuring that these events do not happen in the future. Similarly, the search for the Malaysia Airlines Flight 370, famously downed in the ocean and for which an international search effort was coordinated to find its wreckage, took almost a year to find any source of debris. Next, there exists a large number of unexploded naval ordnance or naval mines scattered throughout the world's oceans. These mines, placed during World War I and World War II, pose major threats to naval ships and regular civilians alike. Finally, there exists a ton of important underwater infrastructure, including internet cables and oil pipelines that need frequent inspection to maintain maximum uptime and reduce repair costs. So it becomes clear that faster survey, reacquisition, and inspection of these submerged objects improves outcomes across multiple critical application areas. So let's take finding an object and mapping it, for example. Traditional remote sensing methods like satellite imagery do not penetrate deep into the ocean to give you high-resolution maps. This prompts the use of autonomous underwater vehicles, as pictured here, and to use specialized sensors like sonar in order to get better imagery. Once an image is found, a diver or ROV can be deployed to get a closer look. In the video on the left, you can see an ROV getting much closer imagery of the object of interest, and in the video on the right, you can see an example of what close-range inspection using imaging sonar looks like. A variety of sensors can be used for this step, including RGB images, LiDAR, or sonar. But we'll be focusing on imaging sonar as a very useful modality due to its long range, ability to discern material types like metal, terrain, or even fish. So we can generalize this process for various other objects of interest as follows. Survey, reacquisition, and inspection is the process of searching an area, performing more detailed acoustic reacquisitions, and then performing close-up inspection using divers or ROVs. The actions of the robot and the data products are shown here. The first step is survey, where an autonomous underwater vehicle is deployed to perform a large area survey. The results from this might be a region proposal at a course level. The next step is reacquisition, where multiple views of the objects are captured using acoustic imagery to better understand what it is. Finally is close-range inspection, where the robot might capture views using imaging sonar in order to produce semantic segmentation or 3D reconstruction, which is useful for downstream tasks. So I just want to go over some of the common sensing modalities so we're all on the same page. So torpedo-style AUVs, like the Ivor 3 shown here, are equipped with a variety of sensors. The primary one we'll be focusing on is side-scan sonar, which an example is shown here. This is primarily used for the survey and reacquisition steps due to its long range and the fact that it can be deployed very easily. Side-scan sonar is a single intensity image of acoustic returns in what is called a waterfall image, and it gets accumulated as the vehicle travels over the terrain. Another class of autonomous underwater vehicle is the ROV, or remotely operated vehicle, which are usually smaller and meant for more close-range inspections. These can be mounted with traditional cameras and also imaging sonar. Now there's a few differences between these sensing modalities, namely that RGB images suffers from local lighting conditions and can be severely degraded due to haze and turbidity of the water. However, imaging sonar is a sound-based sensor and doesn't really fall into these pitfalls. So I wanted to highlight some key differences between side-scan sonar and imaging sonar. So side-scan sonar, as I mentioned before, is accumulated as the vehicle moves. So the left side of the image is the range from the left sonar, the right side is the range from the right sonar, and the vertical height is the distance that the AUV travels. Now at each instance, side-scan sonar only gets a single pixel row, whereas imaging sonar actually gets a 2D image at around 10 to 20 hertz. So you can think that imaging sonar has a lot more information at a given time step compared to side-scan sonar, which makes it useful for close-range inspections. You can see the calibration board clearly in this image, along with the metal railing, which shows up very brightly in imaging sonar, making this very useful for inspection of underwater infrastructures that are made out of metal and various other material types. So this dissertation aims to improve the state of the art in the survey, reacquisition, and inspection pipeline in order to speed up the search for objects at sea. First, we present a novel method for sim-to-real transfer using side-scan sonar images, exhibiting improved performance for segmentation tasks. Then we contribute a new dataset for side-scan sonar segmentation with a diverse set of shipwrecks and environments collected from fieldwork over the course of 5 weeks and 2 years. Third, we contribute a method for active perception for autonomous underwater vehicles, which improves reacquisition accuracy and produces more efficient, multi-view informed reacquisition surveys. Finally, we propose a novel method for scene representation and novel view synthesis using imaging sonars under the Gaussian splatting framework. This work aims to produce more photorealistic imaging sonar renderings for novel view synthesis and higher quality 3D reconstructions. With that said, we'll dive into the first portion of this talk, which is a large area survey. This leads us to our first chapter, which is sim-to-real for side-scan sonar segmentation. This work was published at the British Machine Vision Conference and was supported by a Michigan Robotics Department Fellowship and a NOAA Ocean Exploration Program grant. So although AUVs allow for more scalable and convenient surveys, they still produce a ton of data. It's important to note that a lot of these underwater searches are largely still a manual process. You'll deploy an AUV, collect all the data, and have a group of experts go through it and identify objects of interest. This process is time-consuming for a single survey, but imagine scaling this up to 100 surveys in a day. It takes a lot of time to go through hundreds of gigs of data. This really motivates the application of computer vision methods to this field in order to automate the search for these objects. So if side-scan sonar produces high-resolution, pretty imagery as you've seen before, what makes it a hard modality to work with? First, training deep neural networks for this modality are very difficult due to the lack of datasets for training on. Secondly, you might experience poor generalization in the field because whatever data you collect might not generalize to a new environment, given various terrain types and also object shapes. Finally, there exists sensor-specific phenomena like noise, distortion, and shadowing that make this difficult to deal with. You can see an example of acoustic noise shown here, and also distortions caused by changes in the temperature of the water and also vehicle motion. So the previous wreck was obvious, but can anyone tell me where the object is in this image? It's shown in red. And this really highlights the difficulty of actually finding anything in these images, given that it's a single channel acoustic image. So this work really explores whether we can develop machine learning methods to do this instead, without access to real examples for data-scarce modalities like side-scan sonar. So one potential solution to getting around the data problem here is using synthetic data. So we can produce a synthetic sonar image, and this really offers us the flexibility of domain randomization. We can put in whatever objects we want, we can simulate whatever terrains we want, and generate a ton of labels. However, comparing this to a real image, you might notice that there exists a sim-to-real gap. Namely, the terrain patterns might not be as diverse, and the objects scattering might not be realistic either. So given that side-scan sonar captures a high diversity of environments, there might exist a sim-to-real gap that networks need to address in order to generalize from synthetic data to real data. Another potential idea is to just naively train a semantic segmentation network or a salient object detection network on these synthetic labels and see how well they perform in the real domain. So you can take the synthetic image, pass it through a segmentation model, and then produce predictions and supervise it in a fully supervised manner using the segmentation label. The drawback here is that you aren't actually doing anything to explicitly address the gap between synthetic data and real testing data, so the model might not generalize very well during test time. Another potential way that actually addresses this sim-to-real gap is called unsupervised domain adaptation. So again, we will train a model using synthetic data and their respective labels, but we'll introduce a dataset of unlabeled real data in order to facilitate the transfer from synthetic data to real data. This is where the sim-to-real transfer step happens, and a variety of methods have explored this field in the past. Finally, another potential way you can tackle this problem is thinking of it as an anomaly detection problem. So we have access to a large amount of regular terrain without any objects in it, and these are easy to collect. Suppose we train an anomaly detection model with this so that it learns what normal terrain looks like. During test time, we can give it an anomalous example with an object, and it would be able to tell us that this area is actually anomalous with respect to what we have seen before. This is particularly attractive because it doesn't require any labels in the real data domain and can generalize pretty well given only access to normal examples. So our experiments consider a variety of baselines that all aim to tackle this challenge from a different angle. So PatchCore is a state-of-the-art anomaly detection model. These two models are more unsupervised domain adaptation. HRNet v2 is a state-of-the-art semantic segmentation model, with HRNet v2 real being a slight change in that it is fine-tuned on real data. And we do this to show that despite fine-tuning on real data, synthetic data might be able to outperform. Finally, these two are side-scan sonar-specific models. InspireNet is a salient object detection model. And STARS sorts of falls in that it's trained on synthetic data and is a combination of semantic segmentation and anomaly detection. So our contributions are as follows. We identify that there's a research gap that current methods don't work well for sim-to-real transfer, and we introduce a novel zero-shot sim-to-real segmentation framework called STARS that uses cues from anomaly detection and deformation prediction task for improved segmentation performance. Next, we note that there doesn't exist a current method for generating debris fields of side-scan sonar, and we propose a simple but effective synthetic data generation method that lets us augment our data sets for better sim-to-real transfer. So taking a quick look at how we actually generate the synthetic data, we start by using a traditional graphics environment like Blender, where we can perform ray tracing. And then we're able to actually render out and query the environment for a variety of parameters. And we use the sonar equation to actually render out this image. Finally, we employ a per pixel deformation field, which we use to actually fracture the ship and scatter it across the image. And then we can compose this with a real terrain image in order to produce a synthetic image. So taking a look into more of the architectural side, STARS is composed of two parts. The first is the anomaly branch, which produces features that are generally anomalous with respect to the terrain. The next is a deformation branch, which you pass in a sonar image and it actually predicts the per pixel flow field that generated the debris field. These two are fused with the segmentation head in order to produce the final segmentation map, and the entire network is trained end-to-end. So we conducted fieldwork to collect data from Thunder Bay, Lake Huron, Michigan in order to validate our model. So our data was collected using an Iver 3 autonomous underwater vehicle as shown on the right, which is equipped with side-scan sonar. So here we present some qualitative results compared to baselines. And I've included numbers as well. IOU is a metric where higher is better, and 1 is the highest possible score you can have. So you can see these methods, sometimes they over-segment and sometimes they under-segment. Specifically for PatchCore on the second site, we can see that it significantly over-segments the image. And for more scattered debris fields, you can see that a lot of this is being over-segmented or under-segmented as well. Our method, compared to these other baselines, has quantitatively much higher performance and is able to more accurately segment out these shipwrecks, including smaller bits of debris that are sort of scattered around everywhere. Interestingly, we also compared the performance of STARS, which is trained only on synthetic data, to a network that is fine-tuned on real data. And we find that STARS actually outperforms it, primarily due to the amount of volume and diversity that you can get from synthetic data. So I hope that these results convince you of the effectiveness of STARS in terms of sim-to-real transfer. However, in the field robotics lab, we like testing our work out in the field and not just in the lab on datasets. So in 2023, we took STARS out in the field to test it on completely novel shipwrecks that is never seen before. So the pipeline is as follows. We first deploy the AUV and perform a survey. This usually takes around an hour or more. And then we transfer all the data on the ship back to a GPU-enabled computer. We run STARS through all the data. This takes less than a minute because it's a GPU-accelerated process, and it's not a human actually having to go through this. And finally, we can visualize all these detections in a QGIS framework that makes it easy for people to move around the map and understand what's going on. So what is this actually useful for a robotic sense, right? So with the stars detections, we can produce bounding boxes and also per pixel segmentation labels. We can take this and actually produce what is called a polygonal coverage path, which means it's a path that a robot can use to perform a close-up survey just over the area that the object exists. And using this, we can actually program another robot to take a closer-up survey and collect imagery for reconstruction purposes or whatever downstream tasks you care about. So we note that stars significantly cuts down the amount of time it takes to find objects in side-scan sonar, allowing for accurate detections and with minimal human involvement. So again, going over our contributions, we introduced stars, which uses anomaly detection and a deformation prediction task. And we note that the broader impact is, since this is primarily based in simulation, it can expand to new classes like pipelines, cables, rocks, fish, submarines, etc. Secondly, we introduce a framework for generating diverse debris fields, and we see that future work can simulate debris fields as well in order to improve the fidelity of synthetic data. So we can now continue to the next chapter of this thesis, which is the AI for shipwrecks dataset and benchmark. This was published at the International Journal of Robotics Research and also supported by NOAA. So STARS primarily explored the use of synthetic data due to the data scarcity for this modality. However, it's still useful to have real data sets for benchmarking. So we really see a lack of labeled data for machine learning for side-scan sonar understanding, and this leads us to actually curate and publicly release a side-scan sonar dataset in order to accelerate the progress in naval search. So contributions are as follows. So we identify a research gap that current public side-scan sonar offerings are not large enough and they don't have per pixel segmentation labels. So we curate AI for shipwrecks, which is a new public dataset of 4,261 high-resolution side-scan sonar images, and we also present benchmarking on a variety of state-of-the-art baselines. So some basic details, we have 4,261 total images, over 49 AUV surveys with 28 distinct shipwreck sites with an image size of 1728 by 1728, and 4 terrain-only surveys, which include an additional several kilometers worth of imagery, which might be useful for simulation or other downstream tasks. Here are some examples from our dataset, and you can see the diversity of terrain types and also shipwreck patterns shown here. So one of the interesting things we thought about was how to actually split up this data into a train and test split for a benchmark. So each each shipwreck site, they sort of have various parameters. One of the things we considered was the actual condition of the wreck. So obviously, if you train on very badly degraded wrecks and expect it to generalize later, it might not work very well. So we consulted an expert marine archaeologist to give us scales and ratings for all these wrecks. So some wrecks might be very degraded and sort of fall at the bottom tier. Some of them might be a bit more preserved. Some of them are a bit more complete. And then some of them might be completely fully intact because they're at deeper depths and might have not been as degraded. So we consider this as a potential parameter for splitting up the dataset. We also consider the terrain type. So to identify terrain type clusters, we actually embed all of these terrains into a variational autoencoder's latent space, and we identify several different clusterings of terrains. So we include small scale terrain, patchy terrain, smooth terrain, and also large scale terrain. And we note that a variety of these sites sort of fall under these different terrain type clusters. And we can use this as a potential classification score in order to split this data set up as well. So after these have been identified, we can actually split this up into a train and test split, where these various categories are more or less balanced across it in order to make it more useful to train on one set and actually test on another. Next, I present benchmarking results on a variety of state-of-the-art baselines. And we note that many of these shipwreck sites still pose challenges for these methods, which we hope that researchers in the future explore in order to improve segmentation on finer features. So we released AI for shipwrecks in July, and it's been well received by the marine imaging community. The dataset is hosted on Deep Blue and available to the public. And we've seen several researchers sort of use our dataset in various ways. Some of them convert it into bounding box labels in order to train object detection networks. And some of them have also used it to improve synthetic data generation for their own vision tasks. So in conclusion, we really propose a new dataset that is public and has a variety of shipwreck sites. And the broader impact here is that AI for shipwrecks is accelerating progress in side-scan sonar understanding and can enable scalable naval searches. So we move on to the reacquisition portion of this presentation now. which again is when vehicles are programmed to capture additional views from varying angles of objects that have been identified from the survey stage. So up until now, we discussed challenges with the large area surveys to accelerate discovery of new objects of interest. But now we move on to reacquisition, where targets are revisited in order to understand what they actually are. The work presented here was published in ICRA 2024. And the work in this chapter was done during an internship at the US Naval Research Laboratory in collaboration with Jim McMahon in the Acoustics Division. So this video is taken from some prior fieldwork by the Naval Research Lab collected during field trials in Australia. The blue vehicle finds targets, then tells the yellow vehicle to check them out. You can see in this red box, the yellow vehicle is exhaustively re-inspecting found objects. And you can see that it moves on to the next object after it has inspected the previous one. So this process can be time consuming, and from our experiments, we found that it can be between 40 to 60 minutes per object. So we're really interested in reducing the number of views it takes to actually classify an object. You can imagine for a field with maybe 3 objects, this might be doable, but when there are hundreds of objects in the field, this does not scale very well. So the question we ask is, how can we save time during reacquisition, but still maintain a high classification accuracy? So one thing I want to hammer in is that acoustic imagery varies highly based on the viewing angle. You can see here, which shows a cylindrical target imaged by side scan sonar. As it moves from angle 0 to 225, the scattering patterns and shadow changes drastically. You can imagine for a classifier this being quite confusing. It might have been trained on images from only one angle, but expected to generalize when these objects look differently from other angles. Similarly, because of occlusions, various features can be exposed and also suppressed based on the angle. In the shipwreck, at angle 0, you can see that a lot of the internal workings are not shown, but when you're inspecting it from 180 degrees, you can see that various other parts are illuminated or are actually shown in this image. So currently, ATR algorithms, or automatic target recognition algorithms, need to take in a set of images and produce a classification score. The current approach to use this underwater is first performing a survey stage, which identifies all the locations of objects, and then performing a reacquisition stage, which inspects it exhaustively from various angles in order to classify it. This work sort of proposed an adaptive survey and reacquisition framework, where a robot is able to perform the same lawnmower pattern, but when it detects an object, it breaks off and only inspects the object at the most informative views for classification. The goals here are still to decrease the amount of time it takes for survey and also classify all the objects in a search region, and also improve ATR classifier accuracy. So prior works in robotics have tackled next best view planning and active perception, and a lot of these works fall under the umbrella of informative path planning. Informative path planning aims to optimize trajectories based on some notion of information gain from the environment. But all of these sort of have unique drawbacks. Some of them require specification of an inverse sensor model, which is a function that tells you that relates the state of the robot or how high the robot is to its classification performance. Now you can use some simple models for this, but specifying this for side scan sonar might be very difficult due to the fact that classification accuracy can depend on angles, the class of the object, geometry, and terrain type. So a lot of these classical methods, they don't learn data-driven features, and they actually optimize for something called information gain rather than directly optimizing for classification accuracy. More recent methods exploit reinforcement learning and also deep learning, and so they don't require explicit specification of the sensor model, and they can learn data-driven features. Finally, IMVP, which is a work that's very similar to our work, doesn't require an inverse sensor model, but is still classically based in that it's based off of a Bayes net, and also optimizes for information gain rather than classification accuracy. Our method aims to fill this gap by not requiring an inverse sensor model, learning data-driven features through graph neural networks, and also directly optimizing for classification accuracy rather than any other proxy metric. So our contributions are as follows. The first research gap we identify is that current methods don't optimize classification accuracy directly, leading to worse performance. And we address this by introducing a ViewQ function, which directly optimizes for classification accuracy, outperforming the baselines. We also note that current methods require specification of an inverse sensor model, and we avoid explicitly specifying this by using reinforcement learning instead. Finally, current methods don't fully leverage advancements in deep learning, like graph neural networks, which might be useful for this multi-view classification task. So we propose a novel framework called the angular view graph, which we use to perform next best view planning and classification. So now we can cover some background information. During the surveying stage, we consider a region that is specified by height and width. The number of targets in the region are not known, and the locations are not known either. An 100% coverage of the search region is required, so that we don't miss any objects accidentally. The next stage is reacquisition, and a common pattern to do this is called the object identification pattern. In this animation, the vehicle is inspecting the object at various angles. This is 4 specific angles, but this can be expanded to 6 or 8 depending on the size of the object and the sensor characteristics. You can have a pass length L and also a radius or distance away from the object as well. So the proposed strategy here is not to exhaustively capture all these views, but rather let the robot choose what the most informative views are for making its classification decision. This really will save us time because as the number of objects scales, if we can cut down on the number of views, we can save total time on the survey. So going into the architecture, given a set of side scan views, we pass it through a convolutional neural network and then embed it into a graph neural network framework where the nodes are actually the feature embeddings for each image and the edges are relationships between them. We pass this onto 2 heads, the first of which is a classification head, and the second decides what angle to view next. The decision from the next best view gets put back into the survey and reacquisition planner, and the process repeats again. And it's important to note that this graph framework is actually updated iteratively, so that as you collect more information, you can update the graph as you go along. So for reacquisition policy, we choose to use reinforcement learning. So we have a learn policy that, given a current state, tells you what action to take. And the actions here are, of course, the next best angle to view at, or to stop the reacquisition survey. The environment takes this in and actually tells us what the next state is. So if you choose to capture the angle at 50 degrees, it will give you the image at 50 degrees. This then updates the state, which, as I mentioned before, is the angular view graph itself. And the reward function is particularly important because we give the agent plus 10 points if the classification is correct, minus 10 points if the classification is wrong, and minus 1 for every time step beyond the first correct classification. So if my classifier told me 3 time steps ago the correct classification, I want to penalize every time step afterwards because I want to keep all these surveys as short as possible. So the perception task of interest is multi-class classification. And so we produce a variety of images from 5 particular classes, including cone, rock, cylinder, pyramid, and block. And we generate these using a CUDA-based side-scan sonar simulator. And so we produce 8,000 distinct targets with 6 views each. So the first question we ask is, does the system let you survey faster with higher accuracy? So to understand this, we have a graph here where time is on the x-axis and accuracy is on the y-axis. So the highest possible accuracy you can have is 1. The shortest amount of time you can have is the single pass lawnmower pattern where you don't perform any of these reacquisition surveys. So we see that some of these baselines that use single view classifiers and random policies fall here. Those that use exhaustive policies or inspect all the views have higher accuracy but take longer time. IMVP falls here, so it takes less time and is more accurate than a random policy. And our method falls here, which is significantly less time than baselines and also higher accuracy compared to other baselines. We introduce a variant of our method which uses view GCN. And note that this simply replaces our angular view graph with another graph-based data structure, just to highlight that our graph-based data structure does have improvements over traditional state-of-the-art data structures. So taking a look at some of the reacquisition trajectories, we can see that per object, our method actually inspects it at fewer views, but it still has higher accuracy compared to other baselines. IMVP inspects it at more views, but has lower accuracy. And also the exhaustive reacquisition, of course, inspects it at all 6 views and takes the most amount of time. And you can see here quite shortly that our method ends up finishing this entire survey process first, taking the least amount of time and still maintaining high accuracy. So again, to summarize our contributions, we introduced the viewQ function to address optimizing classifier accuracy directly. And the real impact here is that we achieve higher accuracy in less time, which means vehicles can now scale searches to a larger search region. Secondly, we avoid specifying an inverse sensor model. And this really lets us expand to other parameters. Like suppose I want to now change the survey altitude or various other parameters. I don't need to go back and handcraft a function to do this. I can just let the network learn. Finally, we note that several methods don't leverage advancements in deep learning. And so we introduce a graph-based neural network structure that really lets you exploit the relationship between these various views. And we see that the angular view graph is a useful structure for robotic information gathering, where information is incrementally added on and there is some relationship between the data. Finally, we move on to the inspection portion of this thesis, where close-range imagery is collected to perform a variety of tasks. To recap, the past few chapters have covered large area surveys and reacquisitions, and this next chapter will cover close-range inspection, where robots take a closer look at discovered objects to get more detail. Awesome. So common sensors used for close-up inspection include RGB camera and imaging sonar. However, there are a few differences between them. Imaging sonar can operate in the dark. It doesn't rely on the lighting conditions when the water might be murky or have low visibility. So clearly, imaging sonar has some benefits. So the real question becomes, how can we enable autonomy using this sensing modality that seems robust to a lot of environmental effects? So suppose we deploy a robot and it comes across an object. It captures an imaging sonar image of the object, and now it wonders what to do with it. So there's a few different ways you can approach this. Traditionally, you can use object detection networks in order to create a bounding box for downstream tasks. You can perform semantic segmentation or 3D reconstruction. But the main point here is that perception outputs are required for downstream autonomy algorithms in order to act upon the data that the robot has received. So as a little bit of background, imaging sonar sends acoustic energy into the environment and then listens for echoes. The important thing to note here is that the points at which these echoes come from can be parameterized in spherical coordinates with a range, an azimuth, or elevation angle. So right now it's going about the azimuth axis and now sweeping along the range axis. But it's important to note that the elevation axis is actually collapsed. So all of these returns are summed into one range azimuth bin with no notion of the elevation angle it comes from. And this is called elevation angle ambiguity. This makes imaging sonar particularly difficult to use for 3D reconstruction because 3D information is collapsed into a 2D image. Another important phenomenon I want to highlight is azimuth streaking. So you can see these black lines on the image, and this is a form of receiver saturation, where if there are strong returns at a specific angle, it actually saturates the image and clears out the data at a specific range. So this makes 3D reconstruction difficult by actually lowering the intensities of the return and can also make interpretation difficult for humans. So taking a look at what prior state-of-the-art 3D scene representation methods have done, neural radiance fields introduced a system where multi-view images were used to optimize a neural network in order to produce novel views. So you could train this model using multiple views and then query it at new views in order to perform tasks like 3D reconstruction, denoising, or novel view synthesis. However, the primary drawback here is that NeRFs are computationally expensive to train and also to render. This leads us to a more recent development called Gaussian splatting, where instead of training a neural network, it actually optimizes a set of 3D Gaussians. And the primary benefit here is that it renders and trains much faster than NeRFs. So several prior works have considered using sort of these methods for imaging sonar specifically, but they all have drawbacks. So these first three works, they all model range azimuth images properly, but they can't render out realistic looking sonar, and they don't model these acoustic phenomena like azimuth streaking. More recently, Gaussian splatting frameworks have been used, but they don't model range azimuth images properly either, so they're not physically accurate, and they don't explore modeling these other acoustic phenomena as well. Again, this is more of a camera sonar fusion method, which does model the images properly, but doesn't model higher level acoustic phenomena. Finally, our model aims to actually render out these images in a physically accurate manner and be able to produce realistic looking sonar images, all the while modeling azimuth streaking and unlocking the ability to remove these phenomena from these images. So taking a look at the contributions, our first contribution is a novel 3D Gaussian splatting framework for rasterization and of range azimuth sonar images, enabling novel view synthesis and 3D reconstruction. So we know that current methods also don't model acoustic phenomena like azimuth streaking, and so we develop a novel method for modeling this and also removal of unwanted acoustic phenomena. So quick overview, the input to our method is the sensor pose and a set of 3D Gaussians. And we run this through our range azimuth splatting model, which actually splats it based on the acoustic reflectivity of each Gaussian. Simultaneously, we also splat the azimuth streak probability into a probability image. And we create an adaptive gain function, which allows us to actually combine this with the unsaturated image and create an image that experiences these azimuth streaks. And we're able to train this end-to-end using gradient descent. So going into a bit of the math. This is the traditional sonar volumetric rendering equation. And running through this just says that the intensity at a specific pixel is equal to an integral over all the elevation angles of the sensor and an integral over a small patch at a specific azimuth angle and a small patch at a specific range. And you consider the transmittance, which is the probability of reaching a point without collision along the range, and then also the density of the point. So this relates to us various parameters in 3D space to the image that is actually formed. Now we need to modify this to actually fit it into Gaussian splatting framework. And so we introduced this equation where the intensity is the same. This triple integral gets collapsed into a single sum. And the density at a point is evaluated by actually evaluating these 3D Gaussians. And the transmittance is calculated similarly. We introduce another parameter, which we'll call acoustic reflectance, which tells us, based on material properties, how much energy is reflected back to us. So metal is more highly acoustically reflective compared to rubber or other materials. So quickly going over the azimuth streaking model, given a de-streaked image, each point will have some probability of an azimuth streak occurring. And with this, we can actually create a gain profile, which we can multiply together to simulate these azimuth streaking images. It's important to note that this is particularly useful because all of these parameters can be differentiated. So we can optimize this as we train using just the losses from the images. So in order to evaluate our method, we actually collect a bunch of data. In total, we collect 8 data sets, 4 of which are shown here. You can see the RGB image and the corresponding sonar images shown here as well. Our data collection platform is our trusty Blue ROV vehicle, which has been equipped with an Oculus imaging sonar. And we're able to get sensor poses using the Doppler velocity logger and actually get somewhat accurate sensor poses. So the first result I want to highlight is 3D reconstruction. You can see in the video here a sort of inspection trajectory around a piling. So these concrete pilings are very common in bridges, dams, and other structures, so inspecting it is quite useful. You can see the ground truth 3D reconstruction shown below. DSC, which is a state-of-the-art 3D reconstruction method, is unable to actually reconstruct anything that is of use, whereas our method does give us something that looks much closer to the piling, and is able to capture this 3D structure as well. So another interesting thing I'd like to share is novel view synthesis. So this is the actual captured trajectory shown in green. And you can see that it's simply a straight line path through the basin. We can also reanimate this or perform novel view synthesis to simulate sort of an undulating trajectory that might be due to wavy conditions or whatever. And you can see that this produces realistic renders from various views. For the piling, we have a pretty traditional orbit path around the piling, and we can simulate this to have a path that is further back in order to perform data augmentation and re-rendering. So the important thing is that SonarSplat allows for high fidelity image synthesis from novel views. Taking a closer look and comparing this to baselines, you can see that baselines are unable to produce any realistic sonar image rendering. And zooming in, we can see that we're able to even capture finer details in the image, which is useful for generating realistic sonar renderings. Quantitatively, we also evaluate all the standard image synthesis metrics, and we find that SonarSplat is able to outperform all baselines in this task as well. So possibly the most interesting result is de-streaking. So we conduct experiments on two various object-centric data sets, including the rock and the infrastructure. And we capture data that exhibits these azimuth streak phenomena. SonarSplat is able to also perform novel view synthesis of this, but most interestingly, we can undo all of all of the azimuth streaking here in order to provide restored images with higher visibility. Specifically, you can see that finer details like those on the right side of this image are restored, which might be useful for downstream tasks and interpretability as well. So in conclusion, we note that current methods cannot produce realistic imaging sonar, so we introduce a 3D Gaussian splatting framework. And we see that this will lead to higher quality 3D reconstructions, which will enable autonomous mapping and inspection, whereas novel view synthesis really enables higher quality data generation. Finally, we also note that a lot of these methods don't model azimuth streaking in their models. So we develop a azimuth streaking framework, and we note that de-streaking will improve visibility for downstream tasks as well. So in conclusion, this dissertation aimed to improve the state of the art in survey, reacquisition, and inspection. So first, we presented a sim-to-real transfer method for side-scan sonar, which allows for training only in simulation and generalizing well to real data. We also introduced a novel side-scan sonar dataset for the community. Then we moved on to adaptive reacquisition in order to speed up the search for objects at sea and make these searches more scalable. And finally, we explored 3D reconstruction, denoising, and novel view synthesis for imaging sonar, producing higher quality 3D reconstructions and data generation. So some future possibilities I'd like to consider that this thesis might help build include multi-agent algorithms, where instead of having one vehicle go out and survey, we can split it up into multiple vehicles, making this a more scalable problem. But most importantly, communication between vehicles, which is difficult underwater, in order to increase the collaboration between these robots. Secondly, we can think about efficiency. With the introduction of GPUs and embedded computers, we have access to a lot more edge compute than we did before. So efficiency measures that allow for real-time mapping and reconstruction are useful for robots to take decisions by themselves with minimum human involvement. Finally, an interesting avenue is sensor fusion, where we might be able to get the best of both worlds by fusing camera data and sonar data to produce higher quality reconstructions that are also robust to environmental conditions. I hope to see some more exciting work coming out of the Frog Lab and the community in the future, knowing that we're already exploring some of these avenues currently. So here are some of the publications I contributed to during my PhD, including those that did not directly go into this thesis as well. Now we can move on to the fun part, which is the acknowledgments. So the first group of people I'd like to acknowledge are the committee members. I think someone told me that the hardest part is actually getting everyone to collaborate and finalize a date, and I think that was definitely hard, so I appreciate everyone's cooperation in this aspect. Also, robotics department staff, and I think Denise has saved me multiple times in terms of my graduation timeline, so I'd like to thank her specifically. Next are all my wonderful lab mates who have helped me collect fieldwork data, run through baselines, and done a bunch of nasty work that thankfully we were all in it together, so we were able to get done properly. And finally, a bunch of external collaborators, including Wayne from Thunder Bay National Marine Sanctuary, Karina, and everyone else who helped with collecting this data set and making all this work. I'd also like to acknowledge the funding agencies, without whom none of this work would be possible, of course. So great thanks there. Quickly gonna run through some fun acknowledgements. I'd like to acknowledge all the friends I've made along the way. That really made this PhD program really exciting and fun to take part in. I learned a ton from them, so I totally enjoy the community that has been built in the robotics department. So totally, this would not have been possible without you guys. Next, I'd like to acknowledge my family, a lot of whom have flown from India to be here, including my parents. Oh, my grandparents. So I'd just like to acknowledge everyone who has supported me along the way. And I look forward to making you guys proud in the future. Finally, I'd like a specific shout out to my mom, who has sort of been my #1 fan from the start. I remember since elementary school, she's just been signing me up for and driving me around to a bunch of competitions. Initially, I found it annoying, but I started to enjoy it a lot. So she's actively been coaching and participating in a lot of these competitions, and has sort of been there from day one. So I just wanted to shout out and say that I hope to make you proud as well in the future. So thank you.
Thank you.
Yep. Now I'll open the floor to any questions.